Welcome back to second part of lecture 9, CFD and parallel computing of the high performance computing advanced scientific computing course. In first part we had some discussion about the CFD model for turbulent flow. And then in second part, we will have some example which present the high performance computing in the CFD and its requirement. Let's start with domain decomposition. Indeed, when we are using the CFD in parallel computing, we need to decompose the domain of the problem. The problem could be 2D or 3D. And in fact, when we say we need to do the composition, we divide the domain between different number of the processor. And with parallel computing, we reduce the time of the computing. However, it depends to the size of the problem and the HPC resources that is available. Let's look on this example. As you can see here, the domain it's decomposed between 6 processors, processor 1, 2, 3, 4, 5, and 6, and about the subdomain between the processor. We need to pay attention that usually the grid must overlap, and for example, when we have these points on the subdomain of processor 1 and processor 2, it's required to swap the boundary data between these two subdomains and update the solution. Regarding the memory, when we look on this type of the problem, if we want solve this type of the problem with very large grid, we can say in 2 dimension we have 20,000 by 20,000. The storage requirement, the memory, it will be 6.4 gigabyte. I can see how it's calculated. We have the grid point, byte per number, and number per node. Usually these would not fit to a RAM of one node, and therefore we had to divide the problem between several processors. This is just example which present the visualization how we decompose the domain of the problem for parallel computing. Just to remind you, in the open form, the introduction on the open form, lecture 4.2 and also 4.3, which we use the VScale cloud computing. With the example presented on that lecture, we used this capability to decompose the domain of the problem. The example we had in the open form, it was 2D, and on the example of the real scale cloud computing was 3D, and decomposition is used to divide the domain to the subdomain between number of the processors. Indeed, when we are using the parallel computing, we need to determine some fact, how the processors are connected. We need to take decision. How the paper data to be sent if it is not continuous in memory, how to transfer the data in the right order so the data is there when needed. This requirement must be covered in the structure of the program. In message passing, the processor explicitly send and receive data. For the generic form, send include the address, link, destination, and tag, and the receives also is include the address, link, source, tag, and action. And when if we look here, we have the example of the sequence of the structure of the program. We need to initialize the parallelization, determine the setup, including number of the processor and connectivity, and we determine the size if it's master, broadcast parameters, the time, max step, swap data, and gather the data in the end and end the parallelization. So this is the sequence of the program we need to do to parallel computing. Uh, Regarding the measurement, how have successful parallelization is the speed up. Usually we calculate the time for one processor, time for or to time for p processor, and we will see the speed up. The perfect speed up use this definition, which should be n and which t over t to over n, and we can see the speed up and the performance of the parallel computing. So as is expected on this definition, the performance decreases as n increases. For the MPI message passing interface, and you had the detail in the lecture from the previous talk. We know the MPI is a library, not a language, so it consists of the subroutine that are called from different languages. For example, in the CFD community, usually the Fortran, and C or C++, it's used to facilitate publication of programs. And the MPI is designed for the message passing model, so it's important to mm, point to this concept, which usually general the structure of the MPI parallel program is include the initialize of the MPI, identity of the each processor, number of the processor, and then we have the actual code on the structure and ending the MPI. This is the we can say some point when we use the MPI on the CFD using the parallel computing. If we want to present the step shortly, first we have the exchanging data. Data transfer need to be synchronized. You have the different approach of this one: the blocking send, ordered send receive, buffered send, and no block I send. And then we need to send information to all processor, which is usually broadcast. Then and send and receive the information. In the third step, usually we set up the communicator for a Cartesian grid, and you had some example of this application. Then in the last part, we have the timing of the program, and ending the section with derived data types. So this is very short presentation of the step when we're using the MPI. However, you had example, and you will have a final project also regarding the communicator for the Cartesian grid. So far, we presented the concept of the turbulent flow, why it is important, and why it's required to use the high performance computing. Because of the complexity, because of the computing, we need to use the file. Also, we need to pay attention to some techniques and some points to use the parallel computing efficiently. That means we need to have a speed up and also keep the accuracy of the result. And of course, there are much detail when we using it practically. In the practical example, we will see how we deal with these issues. Then now let's see how we see the effect of the HPC on the CFD application and what its impact. For example, here in this slide, you see there are two simulation of the exchanger. The first one, left hand side, is it took 12 hours for the result, 6 hours for meshing, and 6 hours to run on 16 1000 core. The right hand side is took 3 days for the result, which mostly on the machine. So we can see here we have the HPC resources, but you see how long time it's taken to deal with the CFD simulation. And we can say for this size of the problem, without HPC, it's so difficult to make simulation and could be able to get result for this kind of the problem. Then for the large problem and turbulent region problem, to use a CFD, HPC resources is essential. Now let's have some example of the RANs, LES, and DNS, and have some comparison regarding the result and also the cost. Right hand side is example of the application of the large eddy simulation and RANs, which used for a different condition. Firstly, we should mention that the RANs about 10 to 5 times cheaper than LES. So it's regarding the cost, it's remarkable. Regarding the result for different location, we see for Z 0.5 and Z 0.95. The result from the LES in a green color and the red color is the RANs. We can see for the first one, when Z is 0.5, the result of the LES and the RANs so close together and they match, and we can say RANs it's provide a proper result. But when we look on the second one, which has a different coordinates, the result from RANs in some point provide different result. And these difference sometimes impact the design, and it's required some time to calibrate the RANs simulation with the result from the LES or DNS. Also, from some literature, it's proved that when solving the problem with a specified condition and then changing some geometry, RANs it doesn't get the change of the geometry, and we can say it can see this difference. So sometimes we need to check the result of the RANs, for example, with LES, and make some correction or calibration for the RANs model. However, we know the RANs is too much cheaper than LES. Another example is the left-hand side. It's from sublaminar drag on the curved path flow. In this example also, there were experiment there were results from the experiment and also the simulation of the RANs. RANs presented in some point the drag 10% reduction, which is not correct, and then to correct the RANs model and make a calibration, they use the DNS result in this regard. So in this slide, these two examples presenting us the capability and the result of the RANs in two examples. However, it seems rather than the accuracy, in sometimes the RANs not able to cover some information of the problem domain. And always it's required to check the result, especially with the experiment if possible, or with LES or DNS. Here we're presenting some other example from the turbulence. The right hand side is example from the comparison, the boundary layer and initial condition for the injection, in the engine, we can see here the difference between the LES and DNS. To point to the graph that was presenting the range of the scale that covered with LES and DNS. If you remember, LES covered much less range than the LES, especially for inertial range, which is included in the DNS. Therefore, when we are using these two models, we can see in this presentation the head flux of the cylinder presenting the different scale size. There are two presentations, and we can see how much difference between the scale of this structure, too small and fine grid required to get this information. So it's mean for some reason to see the detail of the problem. Of course, DNS presenting much more detail for this kind of the problem. The another example in the left hand side, it's DNS of the flow around a wing section at moderate Reynolds number. When we have the zoom on this simulation, we can see how many different sizes of the structure or eddies is available in this simulation. Of course, without DNS, we cannot get all of these different scale, and it's showing the difference of this presentation. We can say the large eddy simulation and DNS rely on a very little modeling and are therefore able to capture many features of the turbulent flow. However, when we need to have a simulation for broad range of the scale, we need to access to parallel computing, because to get the all scale, we need to have a fine grid, and the size of the computation, it will be too high. Here we need to point to regarding the 2D simulation. On some point prior to the 80s, the majority of electrical was simulation were 2D. However, the 2D simulation does not applicable for turbulent flow, because turbulent flow, it's a three-dimensional phenomenon. To be able to simulate the turbulent flow and capture all the information of the flow, it's required to have 3D simulation. This statement is very important about the turbulent flow. That means when in some studies, currently there are some simulation using 2D to study the turbulence flow. However, this type of the problem only focus on a specific properties that is possible to study it in 3D, but the turbulence flow generally is three-dimensional phenomena and require to have 3D simulation. And without 2D simulation, we cannot capture all the properties and information of the turbulent flow. In this example, as you can see, the Reynolds number is 400,000 and angle of attack is 5. 3.2 billion grid points is created, and locally structured data and globally unstructured mesh, which presented this great visualization of this simulation. In the CFD, when we are using the parallelism, sometimes the high order method helping to deal with the error. For example, this statement, high order method can efficiently deliver small dispersion errors, which is required. Also, when we are using the parallelism in the CFD, we should look at deeply and what we are looking at it. When we say high order, reduction in problem size and hopefully reduce the cost also. When we have a fast multi-level solver, the coarse grid solve is a big challenge in the parallel. So we need to pay attention to this. And when we ask more parallelization, how much more and how will it will impact our solution? In this regard, we are presenting here example from the studies that show how we can make the more parallelism and where is the optimum point for that. It's for the DNS, direct numerical simulation cost. In this example, it composed of 3.9 million elements with order number 6, which means there are 840 million points in the model, and using 131,072 cores for 100 hours. Then the question is, if we run it faster, do we need a better algorithm or more parallelism? Which one is required to deal with the speed up? And when we're solving faster, it will impact our solution also. This is required to considered when we are using the parallelism for the CFD problem. Then if we want to see the more parallelism is effective, for this example, as we said, there are 3.9 million elements. The max value for the processor is 3.9 million. If we want to look on the point per processor, there are 216. But how about the number, these point per processor? Is it too low? Why? We need to back on the information of the system. These simulations run on the mirror supercomputer from the Argonne National Laboratory, and when they're looking on the information, the envelope analysis suggests a minimum of the point per processor to be 2000 per MPI rank to realize 50% parallel efficiency. So it's important to be aware of the parallel efficiency of the system because different architecture of the system has a different parallel efficiency, and that's why many studies working on the different structure and checking the efficiency of the parallelism. For the current simulation, there are 814 million divided by 262,144 processor, which led to 3,200 point per processor, which means it's much more than 2000 points, which is essential. As the suggestion said, the minimum should be 2000 points, but here we have 3200. Then we can look at the efficiency, the parallel efficiency, and see how it's working. It's used here, it's presenting when we're using 1 million rank. The parallel efficiency is 60%. And the presenter also show when using one process per core or 2 process per core, depend on the point per MPI rank, and we can see here the result. It's show when using the full number of the core, the efficiency reached 60%. But before that, for example, when is 262, 144, it's upper, and also when it go to 138, 31, and 72 also it's upper, which is the blue line in this graph. Then here this graph presenting us how much when we're using different number of the processor for parallelism, it could be impact the efficiency. Then this port is requirement for the parallelism, and from these concepts we can understand how much more parallelism is required. And sometimes with more parallelism, maybe we will reduce the efficiency, which is important point, and it's necessary to consider it in the parallel computing. And this is the example to display the effect of the GPUs in the CFD. Let's point to the concept about the n sub half, which is available in the CFD simulation. It's related to the time between the node when the value of the sub half is presenting the performance reach half of its peak for your application. Then it's relevant to the time step, and it's make the computation need more HPC computing resources. However, here you can see the example of the n sub half. It's with a GPU of the Titan, and with this example, we see when there are 1 GPU, 2 GPU, 4 GPU, and 8 GPU, how the speed up increase and the time of the computing reduce. We see with number of the grid point when they are 14, and the GPU 8 has a better computing time than others. How in the beginning we can see maybe when we have a more number of the GPU, it has a impact and doesn't help in the computing. But we see when it gets better when we increase the number of the grid points. So this is the impact of the GPU, and of course we know the GPU in the parallel computing, helping to get the speed up. If you want to make a summary of the good performance for the CFD application with high performance computing resources, firstly, we need to select between the model for the turbulent flow, RANS versus LES, which is also about the cost, how much we can save, each provide the proper result. And we saw the example that sometimes RANS cannot capture the detail of the problem, but if the RANS appropriate, of course, it's much cheaper, and we can save 10 to 4 to 5 time saving if instead to using the LES. Regarding the discretization, also depend of the method we are using and the solver, we can have a faster solution. Regarding the HPC, it's required to know what the number of the node and processor to make the efficient performance of the high performance computing. And this is also include the model used from the, for example, DNS, RANS, or LES, and also regarding the architecture of the HPC system that you're using to know the minimum number required to provide sufficient efficiency based off the point per processor. Here we finish the part 2 of the lecture 9, which we talked about application of the parallel computing in the CFD, particularly about the model of the turbulent flow, which is much costly than other CFD application, the laminar regime. In the end, there is a video I suggest you to watch it, which is regarding the wind turbine simulation and how it's helping in this area to understand this phenomena, because in the wind turbine especially there is a wake loss effect, which is important to have a layout and increase the efficiency of the wind farm. And hopefully you enjoy this video. Regarding the talk about this course, we point to some important technique and approaches and some note we need to pay attention when we're running the CFD simulation. And of course, in the next lecture when we're running the open form and the parallel computing, we will talk practically about this point. And then we will continue in next lecture, and see you next time. Thank you.